We have here with us Hans Ehm. He is head of supply chain innovation at Infineon, and Jeanette Lorenz. She is senior scientist at Fraunhofer-Institut for Cognitive Systems. They will present to us their project QuaST. It aims to build a bridge from industrial use cases or challenges to quantum solutions. In this talk, solutions using an example from the semiconductor industry will be presented. Quantum computers that can enable or help to optimize extremely complex supply chain processes. And we're happy to hear on the potential of quantum computing in that area from you too. Thank you so much for being here.
Many thanks for the introduction. So I even can kind of spare you the introduction to our topic. Now I'm very happy that in fact Hans Ehm present very detailed use case from Infineon. So we will start the presentation, and after that I will then explain in quite some detail on how we would like to tackle this challenge that Hans is going to present.
Jeanette, thank you very much for the introduction, and it's my pleasure now to bring you a bit into the semiconductor world. So for that, I have prepared a semiconductor, which you see here on the left side. And just looking at a very small spot on this semiconductor and amplifying that a little bit and shoot out the active area by a laser, so you can look a little bit into the semiconductor. As a comparison, I have here the size of a human hair. And all what is really relevant from a semiconductor is here on the third dimension. So everything what you see here, and here you see the transistor, and everything which is green are the metal lines bringing the electrons fast to the transistor, so we have fast switching speed here. To build up this three-dimensional structure, we use about 1,000 process steps, always going back to lithography. And this takes, even if our production sites work on 365 days, 7 days, 24 hours a day, this takes 3 to 6 months. And in the fab, it is important to have a good yield and have a stable supply. Some of the processes are not done by ourselves. Some are done by subcontractors or silicon foundries, or some of the processes are only available once in the world. So we actually talk indeed about a global supply chain, and this global supply chain goes when we talk from the switching speed from nanoseconds and to years for planning because of the long cycle time, and from nanometers, if we look at the gate oxide, for example, up to thousands of kilometers when we look at our global supply chain. So in this dimension we are operating, and therefore, of course, you can imagine that optimization is an important topic. So when it comes to optimization and with this long cycle time and the fluctuating demand, you can imagine that it is needed to be flexible. And for that, we built up a system where on a daily basis, around a couple of thousand bottlenecks from our factories meet a couple of 10,000 demand elements, and in a supply planning, an ATP is provided. ATP is an available to promise. So what comes to the warehouses, what comes to the distribution centers, but is not there yet. So we have a couple of 10,000 ATPs, and more than 1 million orders are in the system. They are reconfirmed on a daily basis. Most of them are reconfirmed than yesterday. Of course, some of them, and therefore we do all the effort, get an earlier confirmation, so earlier to the due date of the customer, and as a collateral damage, some are also later. And when we look at the supply chain with plan, source, make, and deliver, this flexibility in the planning system is basically built up in this intermediate area between a very long-term 5 years min-max plan and a manufacturing execution on the second level. And in here, and in the next slide, I show the challenges here. What I showed on the slide before, a couple of thousand demand elements coming from orders and VMI forecasts, but also the planned target stocks on the die bank, on the distribution center, wherever we do a distribution, wherever we do a distribution into different areas. There we have also stocking points, and a couple of global bottleneck capacities came to this advanced planning system. This advanced planning system delivers the ATP, and the order management has about 1 million order reconfirmations at a day. Then when we look here, what are the challenges? So we have on the one side the challenge of the production scheduling. So this is usually called a chop shop problem. Then we have here the capacity demand match. That's the ATP generation. And we have here, once we have the ATPs, the usage of the ATPs, that's the order, and ATPs, that's the ATP usage. So this one we are calling here a multiple matching problem or a multiple knapsack problem. This one here is a chop shop problem. And here we again have multiple matching knapsack problems. So those are in this area. Chop shop problems are to find the right sequence of a chop. This one can be classically done, but it also can be done via quantum computation. And though this sounds now all quite complex, but we also found an easy representation of this matching problem or multiple knapsack. And for that one, we said, okay, it's an optimization problem where we have a goal function, and into the goal function also putting in the constraints when we talk about quantum annealing, or do it with universal quantum computing. And this problem here just replicated with 2 demands and 2 resources. This one is not only where we have thousands of resources and thousands of demands. This one we can also do in a smaller scale. Now for quantum computation, of course, the potential which we have here, that we can do much more than we can do with normal computation. And the 3 bullets I showed before may have also the potential to be done in once. But now let's look where we are in reality with the quality of our hardware and of our software. So we replicated this simple, this big problem which we have in semiconductor supply chain to a much easier one, which we have now during Corona. We have a certain number of people that need seats. Not everyone can be used. There is a favorite seat. And if you look at that and then applied this for different areas, applying it for a simulator, applying it for a real hardware, applying it for a simulator, and using a quantum annealer, and do this without any optimization or error correction, we recognize that the quantum annealer is good. So it finds from the simple problem the correct solution. As a simulator, okay, if you run it more often, then also it's clear if you run the hardware without any optimization and error correction, the current topics even fail on this level. And therefore, I'm very, very happy that we can join now. We could join now the Fraunhofer. We can join now the QuaST consortium with all this Fraunhofer brain and also superior people there who help us to come closer to solutions for our complex problems. And a little bit more about QuaST will come now from Jeanette. Jeanette, I give over to you. I stop sharing and you start sharing for your presentation. Then you also have the movement under control.
Yes, exactly. So thank you. And indeed, I show you now a little bit of what we are really doing, but let's get first a step back. So as you know, optimization problems appear in really many industrial areas. We have just seen one example, but it is also relevant to production, drug development, for example. And the point is here really that already a small improvement that we can reach by using quantum computing assisted solutions may have an enormous impact. even if it is maybe not the ideal solution. However, at the moment, that's not quite possible in practice, and that is because of different reasons. So one problem is, of course, the known limitations in the quantum computing hardware. Other problem is that you need a deep computer science and physics knowledge to really use quantum computing. But the third point, and that's where our project is coming in, is and that then really easy access to potential quantum advantages for the unexperienced industrial end user is missing. And so here we are getting in. And if you look a little bit closer at the problem, then we see that currently the design of quantum algorithm is very uncommon for the classical programmer, even if it is embedded in high-level languages like Python. And then also we find that only a few high-level languages are available, and those are not very optimal in every aspect. But most importantly, the third point is that the software development still needs to be quite hardware aware. So the question is which hardware is to be used, so which chip design, for example, for a given application, then also on how to map a certain quantum algorithm then best onto the hardware that was chosen, and how then to ensure that the quantum computing algorithm really delivers robust and reliable results. And so our vision is that we develop an additional abstraction layer where the end user should only require minimal knowledge about the quantum computing hardware and the quantum computing software, but still then obtain an easy access to a reliable quantum computing assisted solution of the specific application problem, and that by using the quantum computing hardware as efficiently as possible, and in consequence can benefit as early as possible from potential quantum advantages. And this is on how we do that. And we develop different elements over in the software stack. And here we start from a very wide set of optimization problems. Outgoing from these optimization problems, we do an automatic decomposition into smaller parts that are then best suited for either classical or for quantum computers. So we also decide what part of the problems goes onto which system. And for the parts that we have then decided to really move to the quantum computer, we make sure that we have an optimized mapping onto the quantum computing hardware, going down to even co-design ideas. Then for the interaction that we still have between quantum computers and classical computers, given that we work with hybrid algorithm, we make sure that we have an optimized interaction and runtime environment. And then finally, once we have the full pipeline in place, we make sure that we have a evaluation and verification procedure of the solution to the application. So I will now give a few highlights of this pipeline just to tell you a little bit about the innovations that we are doing. And I will in fact start with highlighting this mapping that we do now targeted towards optimization problems. And here we aim to bring the building blocks of the typical optimization algorithm, the QuaST algorithm, optimally on the hardware, using in this case the parity QC architecture, where you can then run part of the algorithm in parallel, and you can also profit from using explicit and implicit constraints in a very clever way, interconnected, so and that you get a more performant solution of the problem. Then the second aspect I would like to highlight is that we work on getting a better interaction between quantum computers and classical systems. And if you have ever really worked with quantum computers, then you know that this is a really very important point, because current quantum computers require hybrid algorithm where you really need to have this exchange between classical system and quantum computers. However, to really get that working, a really close connection between classical system and quantum computing environments is necessary, and that is not really meant in the technical and physical sense. So we need to make sure that we have a direct or virtual environment on the quantum computing control system with a direct communication channel to the quantum computer. And so we are developing new concepts for runtime environments and additions to the typical monolithic total shop ansatz. And we also develop a flexible data environments for the communication of parameters and quantum measurements in hybrid distributed system, which is then similar to the OpenMP and OpenCL in the HPC context. And the third thing that I'm going to highlight is, in fact, that we need to make sure that then the solution to the application is really correct. And as you know, once we start with an algorithm, we first have a really very sophisticated compilation and then consequently also modification of the algorithm before it really ends up on the quantum computing hardware. So the question is then the resulting circuit that we really end up with really correct? And this is in fact a relatively complicated problem. So the first question is, how can we even simulate it to decide if it is correct? And if we do that with, let's say, classical methods, then this ends up with an enormous size of, here in this example, 32 gigabyte. But with using clever data structures, we can get that down considerably to the megabyte order. And this then allows for an efficient simulation. And then in consequence, after having this efficient simulation, we can then also proceed with, in fact, getting into a verification procedure to really make sure that the implementation that ended up on the hardware was really correct. And here you find even some example codes for this already available. So we do our developments towards many different application areas, and these include the examples that was presented, but also include industrial networks or economic analysis or software verification, for example. It is very important for us that we do our developments really targeted, because only then we can really do a very sensible development of the software. And so let me conclude with pointing out that optimization problems really appear everywhere in industrial tasks, but to really make sure that at some point quantum computing algorithms really bring some significant advantage, we need to do developments like we are doing within our project here. And if we get that then working, then we will have an enormous impact, which will result in savings, but also more efficient processes, increased in performance, or even new products in a shorter time to market. Thank you for your attention.
Thank you both very much for the interesting presentation. I think we already saw it. You're our second last talk today, and we're progressing slowly to how quantum computing can connect to the real world, you could say. We had your example, Mr. Ehm, and you, Ms. Lorenz, also presented other application areas. Maybe you can say what would be the next step, or which industry use cases you'd advise on looking into quantum computing more in depth, maybe also in the project you're working on right now.
Yeah, so as I was pointing out, we are looking at many different application examples. In particular, also the networks examples are very interesting. And the point is, for all of these examples, in all of these cases, we first need to work on prototypes. So we need to downscale the problem, and at some point we need to upscale that again. But it is very essential for us that we get it working on these small examples already now. And so we are working here on many parallel tracks. And in consequence, hopefully, we have then also a whole bunch of applications working relatively soon.
Sounds great for the future, I guess. Upscaling, you mentioned it, is already then the next step, I guess. You already have in mind on how to, or the best steps in ensuring that your prototypes then can be scaled up successfully.
Yeah, this again depends very much on the problem, and there is not a general answer. So even on the scientific perspective, one first needs to dive into a precise development of metrics, for example, to do a fair comparison, and then the devel is in the detail. But we will present some guideline within this project.
Yeah, I guess a general answer would be too easy, Mr. Ehm. Maybe your advice on how to, as a company, start to engage with quantum computing. I think you're already quite invested in the topic. So maybe.
I think a little bit from also what I presented, of course, you need a problem where it is worthwhile to think about quantum computation. Probably that is there at many companies. But then, and I think this is also nice in our case, being able to make this problem very small so that we also get comparison, get results. And by this one, you can then scale from the small problem up to what we envision. And I'm glad that we somehow have this roadmap, and I'm of course very glad that we get this support from all our QuaST partners to go for the next step. So looking forward for the future, what the hardware and the algorithm will bring to solve the real big problems.
Sounds great. I think we're all looking very curious into the future, and what I'm taking with from you is starting small for then scaling applications in companies and industries. Thank you so much for your insights.